Hello everyone, I'm Tiantian, a PhD student in Aalborg University. Today I'm going to talk about our new work towards crowd-aware indoor path planning. As we know, indoor route planning queries are among the most fundamental queries underlying indoor location-based services. And today, indoor venues like airports, shopping malls, accommodate more and more people who collectively form crowds that may in turn influence people's routing choices. So in this work, we study two indoor crowd-aware path planning queries. The first one is indoor crowd-aware fastest path query, which is to find a path with the shortest travel time in the presence of crowds. For example, here is the example. From PS to PT, the shortest path is the black one. But it may not be the fastest path because there are so many objects in that partition. These objects may influence people's moving speed or waiting time, which finally influence people's travel time. So the green one may be the fastest path. This kind of query can be used in airports or train stations where people are more sensitive to time. Another query is called indoor least crowded path query, which is to find a path encountering the least objects in a route. For example, during COVID-19 pandemic, people may want to find a path which can avoid human contact as much as possible. Okay, to solve our problems, we propose a unified framework, including indoor crowd model, time-evolving population estimator, and query processing algorithms. Okay, here is the framework. In the bottom layer, it's an indoor crowd model, which is to organize indoor topology and capture indoor partitions, flows, and density. In the middle layer, it's a time-evolving population estimator, which is to derive future time-dependent partitions, flows, or population. Then in the top layer, it's query processing algorithms. We propose 4 algorithms, and all of them can be used for these 2 queries. The difference between these 2 queries is the cost. For FPQ, we evaluate partition passing time at its cost. For LCPQ, we evaluate partition passing contact at its cost. And this framework can be easily extended or reduced to support other kind of indoor path planning. Okay, here is the indoor crowd model. Each vertex represents an indoor partition, and its label includes partition's area, door-to-door distance metrics in that partition and partitions tab, and population information in that partition. And each directed edge is to connect two partitions, and the label for each edge is a door flow function. We design a door flow function based on a classic Poisson distribution. And for using this function, we can get door flow at a future time by using the this distribution, and parameter lambda is not a stable value. It can change with the time. Then we can obtain the outflow and inflow in partition by using the sum of door flows in that partition. Finally, we can calculate the population of a partition by using its current partition minus its outflows and plus its inflow. We propose two exact algorithms to process these two queries. One of them uses global estimator to estimate partitions population globally, and the other one estimates estimates relevant partitions population. And we also propose two approximate algorithms, which uses some strategies to speed up query processing. One of them derive population for just a part of partitions, and another one derives population just at necessary time steps. We conduct extensive experiments on synthetic data and the real data. We also compare our solutions with a baseline method, which uses general time-dependent graph. And we vary different parameters to evaluate our proposed algorithms. Here is a brief result summary. In terms of running time and memory, two approximate searches perform better. And when considering both efficiency and effectiveness, the search algorithm with strategy PP performs best, and strategy NT applies well to the cases where door flows are updated frequently. In this paper, we propose two indoor crowd-aware queries, and we design a unified processing framework. Then we conduct extensive experiments to evaluate our solutions. For future work, we can consider other crowd models like AI models, which can be used to learn crowd distributions and functions from historical data. And we can design an index to further speed up query processing. We can also extend our proposals to support continuous monitoring of the fastest or least crowded passes. That's all. Thank you.